In this class, we're going to take a look at the power rule for integration. So I'm assuming you've already done differentiation by this point, so you'll have learnt the power rule for differentiation. The power rule for integration works literally in reverse. So whereas for differentiation, you multiply by the power and reduce the power by 1, confusingly in integration, you increase the power by 1 and then you divide by the new power. So it's literally the opposite operations. So we're going to take a look at these examples in a moment. We'll chat a little about the notation before we get started, but just a quick reminder, when you're differentiating, so if you had something like, let's say 3x to the power of 4 minus 12x squared, so a polynomial function. It's polynomial functions that we use the power rule for, both in differentiation and integration. The power rule is going to be your primary rule because you're going to see a lot of polynomial type functions. This is the rule to apply. It's the one that you're going to use most often. So with differentiation, we notate the derivative as f dash or f prime of x, and we multiply by the power, which will give us a 12x cubed, and then 24x multiply by the power, reduce the power by 1. When we integrate, because integration is the opposite, the inverse of differentiation, it should be that we take this guy here, apply the integration, and that will end up back where we started. So let's actually just maybe think about that as an example. So if we want to integrate this, then we start by writing down our integral sign. So we're integrating 12x cubed minus 24x, and we put a dx on the end. So the notation is a little confusing at first with integration. This tells you to integrate. It's not saying it's been integrated, it's saying this is your function, integrate it with respect to x. Just know that every time you've got an integral sign, you need a dx. Like, that is just not a valid statement without the dx on the end. You would get marked down for that for sure. Although it's very common when you start integration to forget to put the dx on the end. But just basically think that these guys are paired up. You need one to go along with the other. The way that integration works, it should be that if we integrate that, we end up back where we started before we differentiated. And we're just going to apply the power rule backwards. So we're going to increase the power by 1. So that x cubed goes to an x to the power of 4. And then we're going to divide by that new power. So we're dividing 12 by 4. Or we could just write it out actually as 12 over 4 like that, just to do it in steps. Remember, an x has got an x to the 1 power on it, like secretly. So increasing the power by 1 would mean that that goes up to an x squared, and then divide by the new power. So increase the power by 1, divide by the new power. It's really common when students start integration after having done a bunch of differentiation to part differentiate, part integrate. You will definitely do that. I sometimes do it. It's really common if you're working a question and you get into the detail to just get lost and think, oh, was I differentiating or integrating? But with enough practice and experience, generally you'll get it right, and usually you'll be able to tell quite quickly if you've made a little mistake. So the other weird thing with these is when you integrate, you've got to put a plus c on the end. This is hugely important. This is called the constant of integration. We're not going to get into why we need that right now. Just accept it as another notational thing. So integral of this dx, once you integrate, you get your result plus the c value. You have to put this on every time. It's another thing that you would get marked down for if you don't put it on. Later on in this topic, we're going to figure out more techniques around this, and we're going to find this value for certain function types and certain question types. So we could simplify this just by dividing. So 12 divided by 4 gives you 3x to the 4. 24 divided by 2 gives you 12x squared. So that's taken us back to where we started, but we've got this plus c on the end. Okay, so that's basically your technique. You're applying this in the same way that you applied it in differentiation to functions of the form ax to the n. But of course you could have multiple ax to the n terms. Essentially, it's just polynomial terms that we're applying it to. Okay, so that's kind of what's going on here, and we'll just keep taking those ideas and applying them to these examples here. So the first one, we're just going to go straight into it, increase the power by 1, divide by the new power, and see what we get. So increasing the power by 1, that goes up to an x to the 8, divide by the new power over 8. Remember to put your plus c on the end. Sometimes you'll find it more useful to write this as 1/8 in front of the x term. It just depends on the question type and maybe personal preference. It's good to know that you can write those both ways. I'll just take out the second one and leave it in that first form for now. Okay, having a look at the next one. So same thing again, just increasing the power, which goes up to an x cubed, dividing by the new power, so leaving the 2 as well, dividing by the new power brings that down to 2/3 x cubed, remembering to put your plus c on the end. This one's slightly different because we've got 3 terms. We're just going to integrate them term by term. So the first one, increase the power by 1, it goes up to a 3. We're going to divide by that new power, but we would end up with 3 divided by 3, so you can save a line of work in. I had this kind of extra line of work in here. At first you might need to put those in, eventually you'll just drop them and realise that would end up as x cubed. Otherwise it would just be 3x cubed over 3, but the 3's would cancel. This one here, remember you've got a 1 on there, so when you integrate that, it's very easy with these ones in particular to differentiate them instead of integrating them. So remembering that x is to the power of 1, so when you increase the power it's going to go up to an x squared, divide by the new power, x squared over 2. With differentiation, constant terms, so in other words numbers, they differentiate to 0, so they disappear when you differentiate them. With integration, confusingly, they power back up. So you can imagine this being an x to the power of 0, you're powering that up to a power of 1, so it becomes an x to the 1 divided by 1, which just leaves it with x. If that had been some other number, like a 4, you would end up with 4x. And part of the way to think about that is that if you then differentiate this here, you should get back to that. So the derivative of minus x is minus 1. Okay, you'll get very used to that very quickly because you'll see a lot of those. And then just remembering, I almost forgot there, to put the plus c on the end. Okay, cool, right, so moving on. This guy, slightly different format because it's got negative power. It doesn't matter, you just do the same thing. Powering that up by 1 though, if you increase the power by 1, remember that's going to go to a minus 3 because minus 4 plus 1 is minus 3, so be careful with negative powers. Dividing by that new power becomes dividing by negative 3, so be careful with that as well. And then just writing it like that. Again, if there was a necessity or if you preferred, you could write that as minus 2/3 x to the minus 3 plus c. Quite common in some questions to want to do that. And in fact, let me just take this one out of the way for now to make some space. And in fact, you might eventually want to start writing these, rewriting them with positive powers. So you could, for example, rewrite this as minus 2 over 3x cubed. The reason why you might want to do that is eventually you're going to start substituting numbers in here. If you want to sub it in here, non-calculator, you would need to process that number manually, and you're going to have to really make that a positive power to do that. So going back to the example I had, which I think was 1 over x to the power of 4. So like differentiation, you're going to find integrands that are not, or terms, functions that are not integratable. So you're going to have to put this in an integratable form first. Remember, this is a form we're looking for, ax to the n, so we can't have fractions like that, or terms with the x on the bottom of a fraction, certainly. So we need to take a line of work in just to make this integratable. So we're keeping our integral sign because we're not integrating yet. We're just using one of the indices rules to bring that x to the 4 to the top of the fraction, making it an x to the minus 4. Just like you would do in differentiation, there's nothing really different there. Now it's in a form that can be integrated. In fact, it's very similar to the one above. So we increase the power by 1, so it goes up to an x to the minus 3, and then we divide by the new power, and then we put our good old plus c on the end. And again, if you needed to manipulate this to make it a positive power, you could rewrite it in this format here. So a quick recap of the power rule. So first of all, it's for polynomial functions. So you're going to have multiple or maybe just one term that look like this. Doesn't matter if it's one term or multiple terms, you just apply the integration power rule term by term. Remember, your integral sign does not mean you've already integrated. It's telling you to go ahead and integrate. Make sure it's in a format which is integratable. This one was not. These guys were all fine. And remember to put your plus c on the end.